Hello everyone, welcome back to our YouTube channel Becoming a ROS Developer. I'm Desire, and today we've got Søren, who has just completed the course ROS2 TF. So he'll be giving us a presentation on that. So without any further ado, let me now hand over the platform to him so he can begin his presentation. Alright, whenever you're ready, Søren.
Yes, you can see me and everything.
Yes.
Good. Yes, hello everyone. I'm going to present my real robot project for this TF ROS2 course here at the Construct. The project starts with, we have this course where we have our turtlebot robot in it. And it consists of 3 parts, where the first part is we need to have the robot map this course, and it needs to map the corners and also the obstacles in this course, objects. Then the second part, that is about generating a trajectory waypoint frame, which is a moving transformation frame, which will move around this course. And then the third part is actually having the robot following this waypoint frame around the course, taking one full lap on this course. So before we really start, I need to localize the robot in this map. So I'll just add here a command. So this is a localization algorithm that was given to us in this course. Let's just start this. We'll get our ROS over here. And then first thing is that we need to give this algorithm a pose in the map, estimated pose, and now we know it's here in the bottom. So I'll just say we are around here. And then hopefully something will happen here. Let's see. Not so much. The second thing we can do is we can move the robot with the joystick around and see if this algorithm will start working or not.
Yeah, okay.
Okay, I think I will just restart this one.
Yeah, I thought
this will help us. So sometimes I think when there's issues with this, restarting
will help, yeah.
The code, will help a little bit. Just closing down. A little bit slow.
Yeah. Try closing the whole terminal, so maybe, cutting the whole process.
Take another terminal. I have this just some copy paste here to remember these different launch files.
Alright.
So now we have it again, and then let's see. Pose. Let's see, I will a little bit unsure. Do I need to launch my feature detections, the program also, for this to work?
I doubt it.
So,
I doubt it, yeah.
I can do it. I seem to remember that should not be needed. Let's go back to this one. A little bit around. Try to launch this one. No. strange.
Let's see what's going on there. Okay, so you are trying to localize it. I would suggest you use 2D pose estimate, right? So that one.
Yeah, I'll try to localize it down here. Actually, the laser scan, maybe it's a laser scan. I don't see it. Normally we'll see it having these red dots on the side.
Okay, let's check in the terminal to see if you can, when you echo it there, you get it in the terminal display.
Yeah.
Okay, you can run ROS2 topic echo scan, and let's see.
Yeah, that's ROS2 echo. Is it scan?
Yep.
Like this.
Okay, so we're not getting that data. Okay.
That's the reason why it doesn't localize. And
yeah, probably. Okay.
We need that for for the whole program here.
Yes. Okay. So let's disconnect and then reconnect again and see if we get anything different.
Yeah, I'll just disconnect down here, right, and then.
Yeah.
We also had a little bit of issues with moving in the beginning.
Okay, so let's begin by checking the scan topic if it's publishing any data.
Yeah.
To do nothing.
Get that image.
Okay, let's wait for it a little bit and see. Can you at least move it with the joystick?
Oh, yes.
Okay, it does move. Okay.
This scan, right? It's not like a laser scan or.
Yeah, no.
Else.
Yeah, okay, do ROS2 topic list just to make sure. But normally it's published on scan on its own. Okay, so yeah, okay. And let's check scan status and see.
The scan status?
Yeah. Yeah, just to see if it's ready or if there's anything that it's saying. It's not working. So.
Nice. Okay.
Yeah, let me ask for. Yeah, let me ask for them to restart because I think that's what's going on there. Okay, I'll just pause here quickly.
Yes.
From where you left off, yep.
Okay, so should I go from the beginning?
No, just from where we left off.
Okay, so where we left is I was trying to localize the robot in this map, I'll just actually remove some of these transformation frames. I think it's a little bit crowded with all these, so to have it a little bit more, let's say, lean, I usually just remove some of these so we can, the robot is more clear.
Yeah.
So, but yeah, so now having started this localizer algorithm over here, we give it a 2D post estimate. I can just give it a new one just for us to see. So we know the robot is down here in the corner, so I'll just help the algorithm a little bit, saying here. And then for the algorithm to work, we need to give it a little bit of data, and that we do by moving around. So we have the laser scan topic to give us this laser point. You can see them over here. And when that detects the map and we see the red square of the laser points, starts to aligning with the real map, and we know we have a good alignment.
Yes.
This localization. We're probably around there now. So that means we can start with the part of the first part of this project, which was to map this map the obstacles in this map, and that is the objects we have here and also the 4 corners. So for that, use this one over here. I have written a program in C++ called feature detection service server. Just this line here. So I'll launch that. And what that does is it starts up a server, which and also opens a new ROS here. So we can have one or the other. I don't know. Let's just keep this one. But it starts up a server, and I'll just have this map be aligned to the other one, so it's easier to follow along. Now this and this should be similar. And then to map the obstacles here, I'll start by mapping the corners. So we now start the server, which when I give it send a message to it, either that we want to detect a corner or a object, then we should get a static transformation frame that is shown in the ROS, and I'll just open a new still for this, and source is below, and then we will write this service call for feature detection, and this custom feature detector server. Give it the name of what we want to map. In this case, it can be an object or a corner. In this case, a corner, and then an ID. This is 1. So I'll just shoot this command off, and then it seems like we get a corner, but it's in the wrong place.
Yeah.
So that can happen if the algorithm is not robust enough. So I'll do it one more time using the same feature ID. Let's hope it works. Yeah, now you see the corner frame was moved to the real corner.
Yes.
So I will then continue with the robot to the next corner. And doing this, it uses a laser scanner, the LiDAR on the robot, to actually map this corner. And what I do is I look in a small angle. I think it's plus minus 30 degrees around the corner, and then I look for the furthest point in this range.
Yes.
And I also do a little bit of smoothing of the laser scan by a moving average filter.
Yes. So what happened earlier on? Was it because it was not the angle was not enclosing the corner, and then it just predicted randomly?
I cannot not say for sure why last time, of course.
Yeah.
I look for the furthest point where we also have a difference in. I also take the difference in the distance of the laser scan. So here they're getting further and further away, and now we're getting closer and closer again, right?
Okay.
And that's kind of where it goes from you say, the derivative of the distance getting higher to getting lower.
Yes.
Then that's a corner, and that you can have actually multiple places. You could also, if you have some noise in these samples, have more corners.
Okay.
But that's why I also apply this moving average smoothing filter.
And how do you deal with the discontinuity that happens when you suddenly switch from a, let's say, a positive gradient to a negative one?
Yes, then I map that as a corner, and then of course I can have within the range I'm searching in, plus minus 30 degrees, I can have multiple corners. If I have multiple corners, I'll take the one that has the furthest distance.
Oh, okay. So it's almost
if,
like
I get a corner here and here and here.
Yes.
I will take this one probably because that's the furthest. Okay. But if there's one that is further, that is wrong, then of course it can't take that. I'll just map the second corner here.
All right.
So you see all the corners.
I see.
Sorry? Yeah.
So it's like because of the smoothing that you do, the corner is considered to be like a smooth curve, just very sharp one. I guess I don't know if that makes sense.
No, but the smoothing is more because of the samples can be a little bit noisy. So you can have some samples next to each other, and it's a little bit farther, then it's closer, like that, back and forth. And the smoothing should help on that.
Yeah.
And the smoothing is quite big. I think it's 10 degrees of angle I smooth over samples within 10 degrees. So should actually be quite a lot of smoothing.
Yes.
And normally it also works quite well, but yeah, there can be times where, of course,
but
for some reason, I had some other issues with that the laser scan sometimes returns could be not a number or infinite or even zero. It messes a little bit up with algorithm. And for that reason, I actually filter all the incoming samples for both zero values and infinite and not a number, the last one. So those are actually filtered away before doing the moving average filter and also the derivative of.
Okay. Very nice. Very nice.
Now, I got the third corner. So I'm just move to. I can see this is actually bottom frame, so I'm just this to the map frame, which is the one we are usually using. The real robot. The bottom we are using more for the simulated robot in Gazebo. It's like this, good. And of course, the map frame should be more stable than the bottom frame.
Yeah, definitely.
Due to different issues with wheel encoders, etc. This should be the last corner. Let's see. Yeah. So now we have the four corners with the ID 1, 2, 3, 4. And now I'll continue and map the obstacles or objects. And of course, here it's a different algorithm than the one for the corners. So when we here give also a different command, so basically we just go and change. Say now we don't want the corner, we want to detect the object, and also have an idea on that. Let's see. Zoom in a little bit, so we are still. Just think I feel still a little bit. Too many of these. Okay. So we have some laser points here from the object, and hopefully we will detect that. And for the object, I will try to find the closest object to the robot, but again within a certain angle.
Yeah.
And also, what I do is, if it detects objects that are too far away, I simply discard them, and it will not give a detection.
Okay.
So it needs to be within, I think, 0.5 meter is my setting.
All right.
See if we map object number 2. Yes, it was this one. and continue the last ones. And then I think I'll just map the corners of this wall down here as object.
Okay.
And for this algorithm, I also apply smoothing with the filter before doing detection.
Okay. What filter are you using? Is it the same one as for the one for corners?
Also moving average, but it's not as many samples as for the corner.
Oh, okay. All right.
There's fewer samples because we also, you can say the objects themselves are not consisting of very many samples.
Yeah.
When we look at the laser points from the LiDAR. So fewer samples. And okay, we get the object there. I don't know if I want to. Do you want me to map the last objects also? Or?
No, I think this is good enough. It's definitely good enough. So let's get to the next section.
So yeah. So now we have this. Then as part of this task, there was also that we should map the starting position of the robot. So for that, it's the same command. It's the same server, but it's a robot start. We call it.
Yes.
So I'll do that. It was recorded when this software started, so we'll see the starting position is down here, because when this started, that was the position the robot had.
Okay.
And then the last part of this is actually to save. Now we have all these objects and corners goes into a list or a vector in C++, and to save that vector into a file, into a YAML file, we will again use the same server, but we will give it a save command. So doing this, what is this save command? Yes, execute. So what we have now is all of this has been saved into a file, and let's show quickly how it looks. So so the file is called myframes. I've also saved some earlier versions of it. This one is the one we've just made. So it looks like this, features, and then we have the corners and their coordinates in X, Y. Z is always 0. We have all the corners, and then we have the objects that we mapped in the end, and then the robot start also.
Okay.
So that was the first part of this project. So now I will just close down this feature detector server, and then I will go to the second part, which is actually I'll launch my action server. This is the third part, but before using the action part of it, I will this server is also launching the server we need for section 2. Just to make it a little bit easier, I just launch this. And what this does is it takes this YAML file and loads all the objects into a map frame, and then populate the map again, as you can see here in RVS. So we have basically the corners and the objects, and then on top of that, we now also got this center frame. You can see it here, the center, which should be the center of the map, and that is calculated when I start up this feature detection server. Because what that does, it takes the coordinates of the 4 corners, and then it takes the average of these, which should be the center, and then publishes that as a static transformation frame. So we have that. This one I'm going to use now to create this moving trajectory waypoint frame, which is a made as a square that will use this center frame and then make a square around it with a certain width and height. So basically following, you can say, in the corners here of this map. You can say basically over here, you can say it should start in this corner, then go down here, then over here, then up, then back again. So that is a moving trajectory frame, which I think it's updated with 10 Hertz. And now for starting this, I will give this server a call, and looks like this, a simple trajectory server, and then using this custom service message, and that consists of a width and a height of this square that we are going to publish at, and then a time, and that is in seconds. So 10 here means that it should take 10 seconds for this frame to move one lap in this map. So I'll call this, and then hopefully what we'll see is a moving trajectory frame. See, there we have it.
Yes.
And it moves in a square, and then coming back. I think actually this one needs to be rotated to match the map next to it. So I'll do this one more time. See if it starts up here, this here, and then you see that's a frame called trajectory frame. And then in the third part, what is the idea is that we will have the robot follow this frame for one lap. I think there was one more thing I was going to say. So this. Yeah, of course. The other part of this assignment was to have the robot here shown with physical dimensions. So you can see now there's a robot, not just a frame. Zoom in a little bit at least. So it is part of this task to have the launch file launch what's called the topic that has the robot physicals in it. Basically the robot model, robot description. But I think that was the second part, and then just the third part is to create a action server in ROS that where you send a command to have the robot follow this trajectory frame.
Yes.
And then the action server will then call this, what we just saw, this trajectory server, and start that up and have it moving around one lap. So I will issue the command now for doing that. It looks like this. So action, so you send a goal to the called simple navigation server, and in my goal is similar to what we just saw for the trajectory server. It's a width for the square and then a height, and then here I increase the time to 30 seconds because the robot actually has to move and follow along.
Yes.
And then the feedback is that it will feedback while it's running the distance that it has traveled the robot during this say driving around the map.
Okay.
And in the end it will give us the total distance driven around.
Okay.
So I'll start it and see what happens. So the robot, we have the trajectory frame here, the robot trying to follow, and as you see, it can be a little bit wobbly, especially if the position in the map, the estimation in the map is not stable.
Yes.
But overall, it
seems to be doing well. Yeah.
And then when it's on one round, it stops, and then He was a goal finish, succeeded, and then the total distance in meters has driven.
Right.
So that was the final part of this assignment. And one thing also to mention here is, of course, I need to make a little bit of control to follow this frame. First of all, to do that, I measure the distance between the robot frame and then this target frame, the trajectory frame, and also the angle between the robot and the target frame. And then the further the distance is, the more speed I give speed command I give the robot.
Very nice.
I use a simple proportional control there, so multiplying the distance with a constant, and then so it speed up when it's longer from the trajectory, or slow down if it's close. And the same for the ankle. Start turning when the ankle is higher, and then slowing down if we are close to having the right trajectory towards.
Are you also
are
you also dealing with obstacles in front of the path that the frame is following? Do you have that?
No, I'm not.
Okay.
No, I'm not doing any obstacle avoidance in this at all.
Okay, so
I'm relying on that we are good enough to follow the trajectory frame, which should go around the corners, so we are not hitting these.
Yeah, I see. So you're relying on the fact that we hope the path will be open.
Yeah, exactly.
All right. So tell me one thing. What would you do, right? What would you do in the event that an obstacle is encountered? Like, if you just off the top of your head, how would you implement an algorithm that will help the robot to avoid obstacles in case that it encounters obstacles along the process of following that trajectory?
Yeah. So if it depends on the obstacles that we have already mapped, like the ones we have.
Yeah.
Or it's like a one that drops down.
Let's say the ones that we've mapped.
Yeah. So if it's the one that we have mapped, we could measure the distance from the robot frame and then to these obstacle frames and say if it's lower than something, and maybe also the angle between the frames are in a way that we are actually driving towards it. Let's say the robot is pointing down here and we are going this direction.
Yes.
Then we need to turn until that's not the case, until we have open path in front of us. We could of course also use our laser scanner to do something similar, but for the obstacles we know we could do it like that.
Okay, so the using of the laser scanner will be for obstacles that are not recorded on the map already.
Yeah, that's more for the we don't know about. Yes.
Yeah, I like that. I like that quite a lot. And I think the algorithm might get a little bit complex, but it will definitely do. In my perspective, it will do well. So thank you very much.
You're welcome.
Thank you very much, Søren. So anything else that you wanna speak about with regards to this project?
One thing is, of course, we are doing this project first in a simulated environment in Gazebo, and going from that into the real environment was a big hassle. There's a lot of things that changed. I think the laser starting point, which direction the laser points in on the robot compared to the simulated, is different, and so on. So that's one thing. Also, I think there's a limit to the speed of this robot.
True.
Even though we give it a command that is higher than something, it will not follow it. At least in the simulated world, it's much easier because we need to follow this directory.
Yeah, you can get any speeds you want.
Yes, basically. And also the fact that we are also relying on this localization algorithm here, which is, you could also see during the test, that it's sometimes basically, I think the transformation between the Autumn and the map frame changed a little bit. Then the robot was sent towards that, so it will also start turning and so on. That's of course you could maybe do something in the software that will make it less dependent on that if if it changes, but at least that also you didn't see that in the simulated world at all. It was perfect
clean,
in that
yes.
sense. Yeah.
Yeah.
So
yeah.
and also the laser. I think the laser values I had a lot of problem. As I said, it started to give me a lot of, let's say, was taking this wall and then saying like
Infinite
part of it
values.
was like a zero, like directly in front of the robot, especially for obstacles. That made me give a lot of issues, because if you have something that is zero, that means it's just next to a robot. It will always put the transformation frame for the object on top of the robot.
Yeah.
So before I had that filter for the laser scan, removing all the zero values, and it was not really working in the real world. But in the simulated world, it was never giving me zeros.
Okay, all right. Yeah, it's a very interesting situation, because this is the reality of the real world, right? You don't get perfect data, and I'm very grateful you mentioned how you dealt with it, because we think that's really important for everyone else and for us as roboticists to understand that sometimes you actually need to get tools that you wouldn't need in simulations to actually deal with the realities of having to run them in an actual environment. So yeah, thank you very much.
Yeah, welcome. Thank you.
All right. So congratulations, Søren, and thank you so much for gathering the courage to come and presentation. We had to see
Yeah, thank you, and thank you for providing this course. It's pretty fun to do.
All right, so I'm gonna wrap it up here, and you just okay.
Yeah.
Alright everyone, this was Søren's presentation, and a warm congratulations to him, and would like to encourage all those of you who would like to attempt this project to do so. It might be a little bit steep, but it will definitely aid in your understanding of the way robotics work and how ROS2 and simulation / the real world will relate to each other. So until then, we encourage you to keep pushing.